So, just to revise, so in the last class we continued with our abstract notation for the vectors, operators and so on. Okay. Quantum mechanics, the operators have to be Hermitian because you want to have real observables, right. That is one, and the state vectors have to be square normalizable, right, because it has the interpretation of a probability distribution and the probabilities better add up to 1 basically, right. So, the fact that they be square normalizable implies that these state vectors belong to a abstract space called the Hilbert space, right, and the fact that the operators be Hermitian imply that their eigenvalues will in general be orthogonal and real. Okay. Now, any vector space has this property. In fact, vector space is defined in that way that any state vector I can construct as a linear combination of a set of independent vectors, right. Hermitian matrices have this property that whichever space they span, their eigenvectors will be linearly independent and they can be made orthogonal. Okay. So, eigenvalues of Hermitian matrices give us a good basis to describe any state of the system, right. Okay. Now, in general any Hermitian operator will have eigenvalues, eigenvectors etc., right, and we can choose to represent the state of the quantum system in terms of any of these eigenstates. It may be eigenstate of energy, right, as we did in the case of let us say particle in a box or a free particle, or I can also choose it to be a some other operator, let us say momentum operator or let us say angular momentum operator, right, and they are also equally valid solutions. Okay. Okay. Given this, we know if we choose a state to be the energy eigenstate, how does it evolve in time, right. Okay. Now, if I want to calculate the time evolution of any other state, I just need to take the projection of that state in the energy eigenbasis states, and for each of these energy eigenbasis states I know what is the time evolution etc., right, and we did this explicitly via example of 2 by 2 systems etc., for example. So, is that clear roughly? Okay. So, today we are going to give another example of a one dimensional quantum mechanics problem. It is called the harmonic oscillator. Okay. Of course, classical mechanics, this is the one of the favorite problems to study, right. There is a spring for example, and the Hamiltonian classical mechanics is generally written by 1 by 2m p square plus half kx square, right, where the system has a natural frequency which is omega, which is root over k by m, right. So, this k I can replace in terms of natural frequency and it becomes m omega square. Okay. Or I can alternately also take out 1 by 2m outside and write it as p square plus right. Okay. And this kind of Hamiltonian is typically valid at the bottom of any potential, right. If I had a profile ux which looked like this, then this kind of a Hamiltonian is typically valid here or here or here, no. So, spring forces in general can have cubic quadratic terms also, but at the bottom low energy they will always have a linear force, right, right. Okay. and that is what you want to solve basically, just the linear part of the force, okay, because that is easy to solve. The non-linear part is not that easy to solve, okay. And let us learn the linear part first, then we can think about solving non-linear part, etc. So, is it clear? Okay. Now, let me go to quantum mechanics. I can go to a quantum mechanics, and all I have to do is basically replace this guys by a operator. So, quantum mechanics also this H is operator, and this becomes p square, right, and operators act on state. So, if you really want to think of some numbers, etc., I should multiply by psi on both sides, right. So, this is a quantum mechanical harmonic oscillator problem. Okay. Now, of course, there are two ways to solve this. Okay. We know that in real space, what is the representation of P and what is the representation of X, right. P is minus IH dou by dou X, and this. If I use this, then this becomes a differential equation, right, and I can try to find the solution of the differential equation, right. Okay. I may not know the answer, but for example, I can guess what will be its asymptotic solutions, right, and based on that solution I can guess that it may have a series solution which is of a particular form. Okay. So, for example, I can guess, let us say this equation should have a psi which is of the form e to the power minus alpha x square times some a0 plus a1 x plus a2 x square and so on. Okay. So, this guess, for example, if I write down this equation, etc., and I neglect the energy term, etc., for example, if x is very, very large, then the solution becomes trivial and it turns out to be e to the power minus alpha x square. So, this is what is called the asymptotic solution. Okay. And if I have the asymptotic solution, then I would guess that the asymptotic solution multiplied by a polynomial is generally the solution. Okay. And the typically strategy to follow is I plug this in here, right. So, I have a double derivative or d psi by dx times d psi by dx, so double derivative here. So, this guy will basically connect a2 to a0, right. I have a double derivative and I have a x square. So, x square will make the coefficient of a0 and a2 equal and so on. So, I will get a what is called recursion relations. So, in general an plus 2 will be connected to an, etc., for example. Yes. Yeah, this is E times psi. So, E will be inside somewhere in these alpha constants, etc., for example. Okay. So, this is a typical strategy of solving it using differential equations, etc., for example, right. And this is invariably what you will do in your courses in your colleges, etc., for example. Okay. So, we are not going to follow this method, okay. But okay. So, just to give you answers, if you solve using this method, what you will get is this psi n are what are called Hermite polynomials of order n. Okay. So, let me use let me use a notation L for Hermite polynomials, which is completely counterintuitive because, but H we are already using. Okay. So, you get a Hermite polynomial of order n which is a function of x, etc., for example, right, possibly times some factor, this factor, etc., which I have forgotten. Okay. The details are not that important. Okay. So, these are complicated polynomials unlike sin x which we got in a particle in a box, etc., for example, right. But particle in a box sin x also, for example, is a polynomial in x to all orders, right, x minus x cube by 3 and so on. So, likewise we will get a polynomial with this kind of a prefactor, etc., for example. So, these are called Hermite polynomials. Okay. So, more complicated functions, but they also roughly follow the same principles of orthogonality, completeness of the basis set, any other function I can represent in terms of these, etc., etc. Okay. And for a given psi n, you can find energies which will be given by n plus half h omega, okay, where your n starts to run from 0, 1, 2 and so on. Okay. So, this we are not doing in detail, I am just stating the answer. Okay. We will do it another way, okay, in a while. But before we go there, I just want to highlight, for example, that this is your not a nice symmetric harmonic oscillator. Let us say this was my harmonic oscillator, then the energy levels, for example, E0 will, I will get half h omega. So, E0 will be somewhere here, E1 will be somewhere here, and so on. So, this will be like the harmonic oscillator energy levels. Okay. And if I can actually plot these guys, okay, then the first wave function I will roughly get like this, and we already have some intuition from our particle in a box problem that the first solution does not have any node, it does not cross the 0 line, etc., for example, right. The second solution of course has one node, right. So, which should better be in the center. So, this will be something like this, okay. And the third solution has generally two nodes, right. So, this solution will probably be like this, okay. And outside the well, the probability of having the particle must go to 0, right, slowly maybe, but it has to go to 0, no. This from classical mechanics. If I put a particle in the center, classical mechanics, it cannot go anywhere outside, quantum mechanics will allow it to go a little bit and so on, okay. So, this is roughly the wave function structure and the energy structure, etc., which is very similar to our particle in a box, except that particle in a box had infinite potentials and the wave functions at the boundaries had to be absolutely 0. Yes. Yes, I agree. So, the excellent point. So, plotting the wave function does not make any sense, right. So, I can just say that I am plotting the real part of psi when I make this diagram, okay. Or what I can say is I can plot the mod square psi, okay, but mod square psi cannot be negative, okay. So, if I have to plot mod square psi, so that will look like this roughly. Here it will look like follow this guy, right, mod square being negative becomes positive and so on. Here it will roughly follow this guy. So, these guys are basically mod psi square, okay. So, plotting the wave function does not make sense, real, imaginary. So, I have to think in terms of either real or imaginary, okay, or I can plot mod psi square and see the nodes in that, etc., for example, right. And this of course is very similar to our particle in a box problem, right, except that the wave functions spill over, okay. And this spillover part is particularly peculiar to quantum mechanics. No? Classical mechanics, my particle can never go out of the barrier, okay. Okay. So, this is roughly the story. This is the details of the solution that you will anyway do in your courses, etc., wherever you are doing quantum mechanics. Okay. What I want to focus on is there is another way to solve this problem, okay, which is by means of, let us say, a very smart trick. Okay. And when we are doing first time, smart tricks are not obvious at all. We have to do it brute force way, this way, etc., for example, right. But we have done it 10 times, etc., for example, then we may be able to come up with smart tricks, etc., for example, right, which may offer a lot of additional insights, etc., for example. Okay. So, since this you will anyway see in your coursework, etc., we are going to do it the smart trick way. Okay. Okay. So, I will get rid of this. But I have roughly told you the answer, right, already. Okay. So, this is the differential equation path. We will follow what is called the algebraic path. Okay. So, name is not important, but the idea is, suppose I want to diagonalize this guy, etc., for example, right. Now, this guy looks like a square of two terms, etc. So, I may think of factorizing this, right, but I have to factorize in terms of operators. Okay. Now, it turns out that I may factorize in terms of two operators, and the energy eigenfunctions may be eigenfunctions of those operators also. Then the solution will become very easy. Okay. Okay. So, we do not know a priori, but let us just pursue this path to a certain extent. Okay. Okay. So, let me define quantities A plus minus, which is some factor. Okay. The factor will write down in a while, not important, that is why A plus comes with a minus sign, I, P operator. So, these guys are operators. Okay. So, this I have just defined with the intention that we will diagonalize this guy, etc. Okay. We are trying to factorize, right. Factorize will not solve, we are actually have to diagonalize, right. Now, we will argue that if you factorize this way, then the eigenvalues will help us diagonalizing this problem, etc., for example. Okay. That is the aim. Okay. So, this is clear? Okay. Now, typically I would have done IP plus m omega x times minus IP plus I omega x. I would have multiplied classical mechanics and would have got the answer, etc., right. But in quantum mechanics I have to be more careful. The operators may not commute, for example, no, Px may not be equal to Xp, right. So, let us see, if I multiply, for example, A plus and A minus, what do I get? Okay. To multiply, let me write down these factors also explicitly. Okay. These factors are just to make the final result more nicer. So, this is 2m h omega. Okay. So, h omega is there because h omega we know will be the energy in some sense, right. And if I multiply A dagger A, etc., and divide by root over h omega, then I am basically taking out that factor, making it independent of that, and the 2m is basically coming from here, root 2m basically, right, to get that factor correctly. Okay. So, what is A plus A minus? So, A plus is minus IP, A minus is IP, so I get a P square plus I will get a m square omega square x square, of course. Now, the mixed terms, right. So, A plus is first, so let us say minus I m omega. So, I am multiplying these two guys, I get a P x, sorry, This correct? Okay. So now what is Px minus Xp? Yeah, so commutator, what is this? We calculated in the last class. Xp we calculated was IH bar, right? So this is Px. So this is minus IH bar, okay? So 1 by 2 mhu bar omega so minus plus yeah, fine. So minus and minus will give me plus, I and I will give me a minus. So m omega h bar, that's it, right? Right? Of course, we forgot to write an operator here, etc. for example. Okay? Okay. Now, this guy, with this guy, it's just the Hamiltonian divided by h bar omega, right? So this is just the Hamiltonian operator divided by h bar omega, the first two terms, and I get a minus h bar omega, I cancel, m also cancels out, I get a minus 1 by 2, right? Okay. That gives me the Hamiltonian, the quantum mechanical Hamiltonian. I multiply by h bar omega on all sides, a plus, a minus, minus half, right? Plus half, right? Okay. Thank you. Is that clear? So we have just changed the, in some sense, notation, no? Okay. So this is one. Now of course I could have done it the other way around. I could have written a minus first and a plus later. Okay. So that you can show, for example, if I write in that notation, then that guy becomes a minus a plus minus half. Okay. So this you should be able to show. Okay. Just following these steps. Okay. Okay. Now before we proceed, for example, two small observations. Okay. A plus is the Hermitian of A minus. Okay. So if I do, for example, A minus and I take a dagger, I will get a plus. Okay. And that should be obvious because here in this notation I do not have to do any transpose. So I just have to do a complex conjugate, no? And the plus minus I sign comes only in P, right? So A plus is the Hermitian conjugate of A minus, and A minus is the Hermitian conjugate of okay. So in themselves they are not Hermitian operator. A minus is not a Hermitian operator, right? Its eigenvalue will not be real necessarily, not any observable. Okay. but you see A plus A minus product is a Hermitian operator. It is just a measure of energy minus something, right. So, we have two operators which are themselves not Hermitian, they are Hermitian conjugate of each other and their product is somehow Hermitian, right, which is roughly a measure of energy, etc. for example. Okay. Okay. This was one, and second was basically we can see from here, if I equate these two equations, right, I will get A minus A plus A plus sorry, if I subtract those two equations is equal to 1. Right. Okay. So, this is nothing but the commutator, right. So, this implies A minus A plus commutator is 1. Okay. So, till now we have not solved the problem, we have just written it in a different form, right. From Px notation I came to equally complicated A plus A minus notation, which have some properties etc. for example, right. Okay. Now, the trick is the following, or the claim is the following. Suppose I take a wave function psi, which is an eigenvalue of the Hamiltonian with some energy E. Okay. So, let me write this down just to be more clear. Okay. So, for a given Hamiltonian, I have eigenstate psi, which is an eigenvalue with energy E psi. Okay. And now, I am going to make a claim, which we can prove that A plus psi is an eigenvalue of this guy. Okay. So, H quantum mechanics acting on this state with an eigenvalue E plus H omega, right. So, the vector state must be the same. So, A plus psi. Sorry, something with the dimensions of energy, right. So, this is a claim, we can prove this. Okay. So, A plus is of course, a operator acting on a state will give me a state, and I am playing the new state is an eigenvalue of the Hamiltonian with some increased energy. Okay. And we can easily prove this. How do I prove this? H quantum mechanical I have here, right. I substitute this and I should get, okay. So, I will get rid of this. Okay. So, my claim is that sorry, so this is not the so A plus A minus plus half psi is equal to E psi, right. That is the first statement, and I want to prove that H omega plus half, so my half is A plus psi is equal to E plus H omega psi, right. This is what I want to prove, right. This is the second statement. Okay. Okay. So, let us write down. So, H omega, I get a So, this is A plus A minus A plus. So, I can take out A plus here, let us say. This A plus I have taken outside, I get a minus A plus psi plus half H omega A plus psi, right. I can always do that. Okay. Now, I can use the commutator to write this operator in terms of A plus A minus, right. So, what is this guy? A plus A minus plus 1 minus 1. So, A minus A plus is equal to 1 plus this guy, right. So, this was this LHS, right. Okay, right. Now, from the above equation, I already know that H omega A plus A psi is equal to E minus half psi, right. So, this guy is just E minus half plus 1 psi. So, just this bracket. All I have done is use this equation H omega, which is still outside. So, okay, so should be more careful. Okay. So, H omega A dagger A. So, this A is still outside. Okay. So, A dagger A. Let me write, or just from here, for example, right. So, what is my A dagger A psi is equal to so I am just trying to calculate this guy. So, I divide H omega on this side. So, E by H omega minus half psi, that is all, right, and that is what I want to substitute here basically. Okay. So, A plus E by H omega minus half, and this plus 1 comes from here psi, and this term I have here, right, and I add a H omega A plus outside. Okay. So, H omega of course is a scalar number, right. So, this guy I can multiply inside, I can take it across this operator. Okay. So, H omega will get rid of this, then I will get a minus half H omega psi. Okay. Okay. So, I get a H omega, this guy is a number. So, A dagger I can carry it across, right, energy is a number. Okay. So, let me do that. So, H omega or I can get rid of the H omega, let me just multiply everything. So, E minus half H omega plus H omega A dagger psi plus half H omega A dagger psi, right. Okay. Now, I can easily get rid of this guy and this guy, minus plus A dagger psi, right. So, my LHS is just E plus H omega A dagger psi, which was my right hand side that I wanted to prove, right. Okay. So, this is great, okay, because what it is saying, suppose I start in some given state psi n, let us say, of energy E n, and act on it with A plus, that will take my state to psi n plus 1 with energy E plus n plus 1, where the difference between these two energies is h bar omega. Right, and I can keep doing this. So, A plus acts like a ladder operator. I can start from the lower rung of the energy and climb up the energy ladder by h bar omega, h bar omega, h bar omega, by keep applying A plus. Okay. Now, A minus also must be doing something, right. So, my claim is similar to this, except that if I apply a minus, it becomes a, instead of a raising operator, lowering operator, okay, and it takes the energy to E minus h bar omega A minus. So, this you can prove, this is a homework, let us say. For A plus we proved, so A minus you can prove, okay. Okay. So, that implies two things. I have a set of raising operators and I have a set of lowering operators. So, raising operator and A minus is lowering operator, right. So, if I knew one state, I could know all other states which are above it by applying the raising operator, and all the operators which are states which are below it by applying the lowering operator, right, and I will keep jumping in the sector, for example. Okay. And this already indicates that all my energy levels are separated by the same distance h omega. So, all energy levels are equidistant, etc., etc. Okay. And together they are also called ladder operators. Okay. Now, I have only one problem, I need one state to start with, right. What is my first state to start with? If I can solve for one state, then I would know all the states, etc., for example, right. Okay. Now, my harmonic oscillator starts from 0 energy potential, right. So, there has to be some lower energy below which I cannot go, because generally my total energy cannot be much lower than the, classically it can never be lower than the bottom of the potential energy, right. Quantum mechanically I may have some leeway, etc., for example, but then also I will have to have a bound, right. So, I will have to have some 0 level, let us say, below which I cannot go. Okay. So, I will have to have the lowest rung of the ladder. If this is a ladder, I will have to have some 0 rung below which there is no energy state. Okay. Okay. If below this state there is no, then what happens if I apply A minus psi 0 to it? I can possibly get the same state, that is one answer, or I can possibly get another function which is not a part of the Hilbert space, etc., etc., for example, and that can be 0. Okay. So, same state, for example, may not be consistent, because for other levels also I may get the same state. See, for all other states, if I apply A minus, I am lowering, right. What happens if I act on the lowest state? I cannot get the same state, right. So, I am claiming that if I just apply A minus on the lowest state, it will give me 0. Okay. Okay. So, this is a claim, we have not proved. We have not proved this, right? Okay. But let us say I start with this claim. If I start with this claim, I can find out what is my psi 0 wave function, okay, and I can find out the energy corresponding to that, okay, and I can actually act on that state to show that this is indeed true, right. In science, we always start with the assumption and proceed with the assumption to see that we do not get any contradictions. If we do not get any contradictions, it is fine, right. Okay. So, this is my claim. Okay. Now, if I know this, I can construct psi 0 wave function, for example, okay, just from my differential equation, let us say. Okay. So, what is A minus? So, I p, right. So, A minus was I p plus m omega x, right, and that acting on some psi 0 is equal to 0. So, the differential equation which I can solve. So, p is minus I h dou x. So, dou x m omega x psi 0 is equal to 0, right, and this simple differential equation I can solve to find what is my psi 0, right, and that gives me, for example, dou x of psi 0 is equal to minus m omega x psi 0 or dou psi 0 by psi 0 is equal to minus m omega x dx or log psi 0 by some psi, let us say by some constant, let us say a is equal to e to the power sorry. So, minus m omega x square by 2 h bar we have missed somewhere, right, h bar we have missed. So, there was a h bar, I can divide by h bar 2 h bar, or for example, this gives me psi 0 of x is equal to some a e to the power minus m omega x square by 2 h bar, yeah. Right. So, this is my ground state wave function, etc., for example. Okay. Okay. And a, of course, you can calculate by normalizing this guy, etc., right. And this is why we were taking, for example, when we are writing down the differential equation solution, that the asymptotic form is e to the power minus x square, alpha x square. Okay. Okay. So, this is psi 0, okay. And of course, we saw that if I start from some state psi 0, then I can get to any state by raising operators, etc., for example. Okay. Okay. So, in general, I can write a state which is psi n by working on the state 0 with these raising operators n times. I start from 0, 1 takes me to 1 level, 2 level, 3 level, and so on, right, except that I may have some normalization constants involved. Okay. Okay. Now, it turns out that we can prove what is this normalization constant, etc., for example. Okay. Okay. So, just take my word for it for now, that this normalization constant is 1 by n factorial. Okay. We can prove this, but it will take a bit of time and we are running out of time. Okay. Easy to prove, not difficult. Okay. So, given a state psi 0, I can construct all of these higher states, etc., for example, right. Okay. So, now this construction for the harmonic oscillator problem, all it does is it gives us a different way of finding the solution, eigenstates and eigenfunctions. Okay. Eigenfunctions, we have not found their algebraic representation in the sense that the wave function, Hermite polynomials, etc., for example, right. But as long as I know psi 0 and I have these operators and the properties of these operators, we know they commute, sorry, they do not commute, their commutator is 1, etc., for example. We can always do calculations using this. Okay. Okay. Now, the real advantage of writing it this way is another completely new way of thinking, which is the number, particle number representation. Okay. So, this is a one particle problem, right. Okay. Now, the nth energy level I can think of in a completely different way, that I have one part, suppose I have one particle, I will put it in the one energy level, 0th energy level. I have a second particle, I will put it in another energy level. So, nth energy level is like n particles are occupying the system, right. For one particle I have first energy level, second particle I have second energy level, right. And this A dagger A basically count my, or rather, so this guy A plus A minus, basically when it acts on some state psi n, just gives me n psi n. Okay. With whatever we have done, this you can easily prove. Okay. In fact, yeah. Okay. So, or the proof will easily follow that if you can show, just for example, that the psi 0 corresponds to E 0 is equal to, or it will just take 1 minute, let us just show it. Okay. So, we claim that A minus psi 0 is 0, right. Okay. Now, right, h bar omega. If I want to find what is E 0, then this is the Hamiltonian times E 0 psi 0 gives me E 0 psi 0, right. Now, A bar A minus, when it acts on this guy, gives me 0, right. So, that immediately gives me, for example, that this E 0 is half h bar omega, right. So, the bottom energy we know, half h bar omega, we act on it with raising operators, we go h bar omega, h bar omega, h bar omega. The bottom wave function we know, psi 0 we have calculated. This we already did a normalization to similar problem. You can normalize this, right. You get 1 by pi alpha to the power 4, where alpha is this m omega by 2 h bar, etc., for example. Okay. Okay. So, we know the bottom wave function, bottom energy, and all other states are constructed in terms of these, etc., for example, right. Okay. Now, all that I was trying to say, that based on this you can easily show that A plus A minus gives you n times psi n. Okay. So, this n I can also think like number of particles. First particle I put in one energy level, second particle I put in second energy level, third particle. So, if I am occupying nth energy level, then I have roughly n particles. Okay. And this way of thinking, number representation of particles, etc., for example, is very, very useful when we deal with more than one particles in quantum mechanics, etc. All that we did was one particle, right. But in principle there will be more than one particle. So, solids will have 10 to the power 23 particles roughly, etc., for example. And if we deal with those, then this representation is very, very useful. Okay. Okay. So, that is all I want to say about harmonic oscillator today. Any questions? No? So, this is just a representation. I just said I can think of this problem as n particle problem, and this way of thinking useful when I actually define that problem, many particle problem, etc. for example. Okay. When I go to what is actually called number representation, basis, etc., etc. Okay. Here it is not needed. This problem we could have solved without anything, etc. But the insight that we get by this, that will be very useful when we go to the many particle picture, etc. for example. Okay. Okay. So then that's all we want to do about harmonic oscillator. Okay. And last few minutes I just want to revise the postulates of quantum mechanics. Okay. So we are coming back to the class 1, let's say. So before you go away, we should just revise the postulates of quantum mechanics. Okay. So we'll divide the board into two halves. Let's say classical mechanics, and here I have a quantum mechanics. Okay. Okay. So in classical mechanics, if I have a single particle, its state is described by x and p. Okay. So number one, so state of one particle is described in terms of xt, pt. Right? If I know one particle and this guy is enough to describe its state. Okay. 2, if I have any other dynamical variable of the particle, dynamical variable meaning any other observable related to that particle, total energy, momentum, angular momentum, etc., etc. So any other dynamical variable which I describe as observable. Okay. Let us say q for the observable is generally a function of this x and p, right. Okay. So corresponding to this, in quantum mechanics we get that the state of the system one particle is described by a wave function psi t. This wave function in general can live in a abstract Hilbert space, wave function in Hilbert space, where we of course know that Hilbert space is a vector space of square normalizable functions, etc., etc. Okay. In the background there is a definition of vector space, etc., etc. Okay. All that given this. Now 2, so in quantum mechanics, x and p basically are not dynamical variables, but they become operators. Okay. So x and p are not independent variables. So here the independent variables, right, x and p are independent variables, are not independent variables, but operators. So x goes to x hat, p goes to p hat. Okay. And in a particular basis, which was the real space basis, we had a representation of these guys. So, x hat went to x, which multiplied the wave function etc., for example, right, and p hat went to minus I h dou x, right. This was in a real space representation. Okay. So, I am doing slight cheating here, but let me allow that just to be consistent with what we did in the class. Okay. This is slightly more complicated. Okay. If I have to write a real representation of operator, it should have all the elements. So, I should have x prime etc., for example. So, instead of x it will be delta x minus x prime, and that will complicated matters here etc. But just for simplicity, let us just keep it as it is. Okay. Yes. Okay. So, now any other dynamical variable which was there in classical mechanics, I can have a quantum mechanical version of that. So, q becomes a q hat with x going to x hat and p going to p hat. Okay. There is a slight trick here. See, in classical mechanics the orientation of x and p does not matter, right, but in quantum mechanics the orientation of x and p can matter. So, one has to be very careful while defining this operator. One has to take the orientation such that you get a Hermitian operator finally. Okay. Okay. Operators may not come here, and the simplest thing to do this is whenever I get a product like xp and I am not sure whether x came first or p came first, I can replace it by xp plus px by 2. That generally works. Okay. That way I have already symmetrized the system and guaranteed to give you Hermitian. Okay. Okay. Barring that detail, this is our second postulate, right. Okay. Now, let us continue on this side. Okay. So, the third is about observation. Suppose I have a dynamical variable q in classical mechanics, right, and I do the measurement on the system. So, measurement I am thinking of ideal measurement. I can do the measurement without disturbing the system. Okay. So, classically it is easier to think. Even if I measure the time period of a pendulum, let us say, I assume that my switching on of the timer does not change the period of the pendulum, no, that is so trivial, intuitive, right. Quantum mechanically it may not be true. Okay. Okay. So, ideal measurement. So, ideal I just mean non-invasive. Doing the measurement you are not destroying the system. Okay. Of a dynamical variable q will give you this variable q. If I knew the state of the system, ideal measurement of a system, dynamical system, the state. So, in state, if I knew x and p, then I knew q of x and p, and this will be the result of my measurement, right. All I am saying is classical mechanics, if I knew the velocity and the momentum of the system and I measure linear momentum, I will get p basically, okay, and so on. Okay. The state remains unchanged. Right. So, the system can be unaware of the momentum completely, measurement. It continues to, so a pendulum for example continues to be in its motion with whatever x and p it had, right. Okay. This is where quantum mechanics differs the most. Okay. Suppose a system is in a state psi and I do a measurement of the operator q, right, and q, let us say, is an operator which has eigenvalues qi and eigenvectors given by these vectors qi. Okay. So, in general the eigenvector and the eigenvalues, right. So, if I do a measurement of this qi, I am likely to measure this in one of the eigenstates of qi. Okay. So, measurement of qi will yield an eigenstate of operator q with a certain probability. Quantum mechanical measurement is with the probability so whatever state was there, eigenstate, let us say qi, okay. So, with the probability qi psi mod square, right. We did examples of this. Okay. So, I had the state in some eigenstate, let us say whatever state of the system, I do not know, but if I do a measurement of a particular operator, then I am likely to measure one of the eigenvalues of that operator, okay, with this probability. Okay. So, this is one part of the hypothesis. This is the measurement I get. Now, what happens to the state? So, the state collapses to the eigenstate. To the eigenstate of this q operator, whichever we are measuring basically, right, or we are writing that psi, if you measure, it goes to the state qi. This is the major difference between quantum mechanics and classical mechanics. The act of measurement destroys the state, destroys in the sense destroys initial state and it puts in some other state. Okay. And the fourth one is really simple or trivial, just telling me the state of the system will not work. To describe the dynamics, I also need the equation of motion, right. So, fourth one, if I continue here, for example, equation of motion is given by, for this system, if the Hamiltonian was H classical, then I get x dot is equal to Hamiltonian equation of motion. Sorry? So, x dot is equal to right, and p dot is equal to minus, right. So, let me just write dou p and dou x of H classical, right. And here the dynamics of the state is described by the equation of motion, which is the Schrodinger equation of motion. So, H quantum mechanical psi, where this H quantum mechanical is obtained from this H classical by substituting x goes to x operator, p goes to p operator. These are the postulates of quantum mechanics. Okay. So postulates are something that are the starting point. We cannot prove this really, right? These are the axioms in some sense of quantum mechanics. Okay. So I need to have the concept of some abstract vector in an abstract space, which is a Hilbert space, to describe the system. Okay. Then I need the concept of dynamical variables becoming dynamical operators, Hermitian dynamical operators. Okay. And the expectation value of these will correspond to, in some sense, the measurement, etc. Okay. The most important departure was this, and this was the most painful point, which took quite few years to resolve, etc. For example, which still trouble people. Okay. So classical mechanics, I can do a measurement. I don't destroy the state of the system, right? Pendulum keeps swinging as it was, irrespective of my stopwatch pressing, etc. Quantum mechanically, first my measurement depends on which observable I am observing. Okay. If I observe for position, I will get the state as a position state afterwards. If I observe for momentum, I will get the momentum state afterwards, right, and so on. Okay. And the measurement answer depends on the projection of the initial state along one of the eigenstates of this operator, right, and it is a probabilistic measurement. If I measure it 10 times, I am likely to get different answers, etc. If I do it 1000 times in ensemble average, then I am likely to get a distribution, and the probability distribution of that distribution will be this, right. Okay. More importantly, the state collapses to the eigenstate of Q, okay, if you do a measurement. Okay. So after the state has collapsed, if I do immediately another measurement with the operator Q, I will always find Qi, right, and that is the story of quantum mechanics. The rest all is built on these to do calculations, etc. for example. Okay. Okay. So for example, uncertainty principle is not an axiom. It comes out of consequence of these axioms. Okay. What else? The wave functions be normalizable, or we interpret the wave function as a probability distribution function of finding the electrons. That is another interpretation. That is not required by quantum mechanics. Okay. That is required for our sanity. How do I think of quantum mechanics? I mean, wave function, etc. for example, right? As long as I know that this guy gives me the expectation value this way, I need not have a really interpretation of psi square. I am never really going to measure mod psi square. Okay. And that is it. So that is all I wanted to say about this postulates also today. Okay. Questions? Okay, so let me make that more precise. Suppose I had the state in, I do not know what state was, some arbitrary state, and I want to see what is the probability that this particle is this location. Okay. Somehow I could set up an ideal measurement. Okay. So I will find that this state with some probability, let us say 0.1 or 0.2, is at a given location x. Then the measurement has collapsed the state to a eigenstate of the position operator. So now immediately afterwards, if I do the another measurement, I am likely to of the same measurement, let us say. So I did one measurement which collapsed the wave function, I do another measurement, then the another measurement will give me with 100% probability that the state is here or the particle is here, for example. That is the meaning of collapse.
But you said that before measuring the state of the particle, before that particle can be anywhere.
Particle is in any state, yes.
But after measurement, if I am going to measure some other measurement,
yeah,
particle can be absolutely there.
yes. So the story is one measurement or two measurements. Suppose I do one measurement, The first measurement will give me an arbitrary probability of finding the particle in one of the eigenstates. But suppose I did the same measurement immediately afterwards, that will give me with 100% certainty that the particle is here. Okay, 100% within the limits of the time duration that you take to, but you get the idea, right? Yeah.
100% probability that particle is there. Then
For the second measurement.
then why we look for the assembled average?
First measurement, no? First measurement I don't know the answer. No? First measurement I don't know the answer. And I cannot really do the second measurement without the first measurement. Right? That is infinitesimal small time. Suppose hypothetically you could do that, right? In principle, of course, see, in principle, lot of limits on this are also from our accuracy of how accurate measurements we can do, how ideal measurements we can devise, etc. I am not even going there. I am saying suppose you can do this and you can do it infinitesimally afterwards, no, theoretically, right? In a classroom we can always say that, right? The pain will be when you actually do the real experiment. The particle is oscillating back and forth. Classical mechanically, let's say. Yeah. Okay. So you should answer this question for me. How would you know this? Yeah. So quantum mechanically also we can calculate something which resembles classical mechanics. I can calculate the expectation value of the particle, x of the particle. In fact, that's a good exercise. We always do it when we teach harmonic oscillator. So you should calculate the expectation value of the position operator. See, what we calculated was the eigen functions in the energy state, right? Now let me assume that the particle is in the zeroth state, right? I can always assume that classically also I send it with certain energy, okay? Now for the zeroth energy state, let's say, I can calculate x expectation value. Please calculate that. Time dependent, right? So the time average will be 0, but time dependent will give you a cos omega t or a sin omega t, etc., for example, right? And that's why you say particle is oscillating, or you calculate the momentum. Similar story, right? Okay, so what is Schrodinger's cat experiment? Meaning there is a cat in a box. So there is a box which has cat and probably poison in it. Okay, so there is a. No, why are you saying it opposite? Okay, so Schrodinger's cat. Okay, suppose I have a box. At t is equal to 0, I put a cat in it and poison in it. Okay, and t is equal to till t is equal to 0, I am watching. Okay, and it's a quantum system. T is equal to 0, I put a lid on it. Right. Now you want to say that at t is equal to 1, let's say, even 1 second or something like that. The cat is dead or the cat is alive. How do you know? Yeah, but how do you know? Meaning, so without opening the box, without doing the measurement, can I say whether the cat is alive or dead? So quantum mechanics says that the cat is oscillating between life and death, superposition of all possible wave functions, etc., as time evolves. Right? That's what quantum mechanics is saying. Without doing a measurement, I cannot really say the cat is alive or dead. Yeah. So why is it a failure? That's a feature. No, but answer you will get only after you do a measurement. after you make the wave function collapse. Quantum mechanics tell, for example, so this is exactly same question that we asked in the sense of, suppose I do a measurement of an operator and I find that the expectation value of that operator is C. Now, what was the expectation value of the operator just before C, for example? I cannot really say. No? This is the what is called the orthodox interpretation of quantum mechanics, Copenhagen interpretation, etc., which turns out to be, which we now know is correct actually, based on more precise measurements, etc., after 50 years of, more than 50 years, 70, 80 years of predicting quantum mechanics, etc.
Is the cat really a quantum mechanical system? Because in one of the states, once you measure, suppose you started for the time and you measure,
Yeah.
you don't know where it was before, whether it was alive or dead, and when it died.
Yeah.
But if it's alive, then you know the entire history. It had to be alive before, because it can't go from dead to alive.
No, see, dead and alive, because you are thinking in terms of, for example, our intuition that you cannot come back from dead to alive. Okay. Let me say the state was cat was, or let me replace cat by a particle.
I would say it's sleeping or awake.
Okay, hold on. So let me replace cat by a particle, and life and death by level 1 and level 2. It's a 2-level system. The problem that we did in the class. Okay. So the particle will keep oscillating between these two levels, right? Cos omega t. We calculated, right? The D version of the yesterday's problem was also that. Okay. Now, if you bring your realistic real particle, for example, that state 1 was dead. If you come to state 1, you cannot, I mean, you are finished, 0, right? Then, of course, you cannot map that problem to quantum mechanical problem. Okay. See, the problem is 2-state problem. You are oscillating between these 2 states, and without doing the measurement, I cannot tell what with probability it is in state 1 and state 2. Okay. In my intuition, I cannot have cat with probability something in dead state and probability something in live state, because but quantum mechanically it's allowed. I can oscillate between life and death. Right. So, Schrodinger cat example is built for the general public. Okay. Of course, cat cannot be quantum mechanical most likely, unless its momentum is very high, etc., for example. And you may have other states also. No? Cat may eat a bit of the poison, it may get sick, may not die, etc. But we are not going there. Yeah. So, what was the most nice thing about quantum mechanics, or what is the most, let us say, either anti-intuitive? What is the most troubling thing about quantum mechanics? Sorry? It is not deterministic. Yeah. So, this was also a problem historically. Okay. A lot of people just could not accept that, we can have a theory which is not deterministic, in the sense that if I know xp of the particle now, I cannot predict where it will be in the future. That definitely is one of the problematic things. I completely agree. Okay. So, God does not play dice, for example, right? God is playing dice here, and you have to live with it. Okay. What else is more troubling? So, there are a lot of physical aspects, for example, okay, that I am absolutely not comfortable with. This I am absolutely not comfortable with. You tell me this is completely anti-intuitive, okay, etc., etc., for example. But I don't have any option. This is the way nature is. I can either say that, since this is not intuitive to me, I will not work with this. I will not do any quantum mechanical calculation all my life and go home and sleep. Or, force myself to accept it, right? This is how nature works, and let me use quantum mechanics to do calculations and predict new things, make new stuff, etc., etc. So, the second approach is much better. You use it as a tool to do calculations, right? And the easiest way to get familiar with all this non-intuitive stuff is to start doing calculations. If you do calculations, it will become easier. So, we have a quantum mechanical particle tunneling at the end of the class, tunneling in at the end of the class. Okay. So, that is it for today.